In this video, we'll learn about binary search trees. A binary search tree is a special binary tree that is used for searching purpose. Let us see the definition of a binary search tree. A binary search tree is a binary tree that is either empty or has the following properties. All keys in the left subtree of root are less than the key in the root, and all keys in the right subtree of root are greater than the key in the root, and both left and right subtrees of root are also binary search trees. So this is the recursive definition of a binary search tree. Now let us take an example. In this tree, 70 is the root node, this is the left subtree, this is the right subtree. So we can see all the keys in this left subtree are less than 70 and all the keys in this right subtree are greater than 70. These two subtrees are also binary search trees. So in this subtree, 40 is the root. All the keys here in this left subtree of 40 are less than 40 and all the keys in the right subtree of 40 are greater than 40. Here, the 75 is less than 80 and all the keys here are greater than 80. So in a binary search tree, for any node, the key value in the left child is smaller than the key value in that node and key value in right child is greater than the key value in that node. For example, if we take this node, this left child is smaller than 40 and right child is greater than 40. For this node, this left child is smaller than 89, this right child is greater than 89. Now let's see some more examples of binary search trees. This is a binary search tree. All the keys in this subtree are less than 70. All the keys in this subtree are greater than 70. Now for this subtree, the left subtree is empty. The keys in the right subtree are greater than 35. Similarly for this subtree, this right subtree is empty and all the keys in left subtree are less than 90. This is also a binary search tree. All the keys here are less than 70. Keys here are greater than 70. This is a binary search tree. The right subtree is empty and all the keys in the left subtree are less than 50. For this subtree, all the keys in the left subtree are less than 40. For this subtree, all the keys here are less than 35. Similarly, for this subtree, this 12 is less than 33. This is also a binary search tree. The left subtree is empty and all the keys in the right subtree are greater than 40. This is again a binary search tree. All the keys here are less than 40 and for this subtree all the keys are greater than 20 because all the keys are in the right subtree. For this subtree all the keys are less than 30 because this is only left subtree, and for this subtree this 27 is in the right subtree, so it is greater than 25. Now let us see the implementation of a binary search tree. This is the class node that represents a node of a binary search tree, and this is the class binary search tree. We have taken this reference root that will always refer to the root node of the binary search tree, and in this constructor we are initializing it to null. We'll see both recursive and iterative methods for insertion, searching, deletion, and finding maximum and minimum keys. Now these two methods implement insertion recursively, and this method insert1 implements insertion iteratively. Similarly, these two methods implement searching recursively and this method implements searching iteratively. Similarly, we have other methods. This method implements deletion iteratively, and these are the methods for finding minimum and maximum keys. These methods display, pre-order, in-order, post-order, and hide are all same as in binary tree. In this method main, we are testing different methods of this class. So in the next few lectures, we'll see how to implement insertion, deletion, searching, and finding maximum and minimum keys. A binary search tree is a binary tree. So it can be traversed in the same way a binary tree is traversed. We have already seen how to traverse a binary tree. Now let us traverse this tree in pre-order. We know that in pre-order, first the root is visited, and then the left subtree is traversed, and then the right subtree. So here first we'll visit 70, then 40, 35, 30, 37, then 50, 55, then we come to 80, 75, 89, 82 and 93. Now let's see the in order traversal. In order traversal, first the left subtree is traversed, then the root, and then the right subtree. So here first we'll traverse this 30, 35, 37, 40, then 50, 55, then 70, 75, 80, 82, 89 and 93. So this is the in order traversal for this binary search tree. Now let's see the post order traversal. In post order traversal, first the left subtree is traversed, then the right subtree, and then the root is visited. So here first we'll visit 30, then 37, 35, 55, 50, then 40, then 75, 82, 93, 89, 80, and then at last 70. Now let's see the level order traversal. First, this node at level 0 is visited, then the nodes at level 1, then these nodes at level 2, then these nodes at level 3. So these are all the traversals for this tree. We can see that the in order traversal gives us the keys in ascending order. In this video, we will see how to perform searching in a binary search tree. Suppose X is the key that has to be searched. So we'll start at the root node and move down the tree. And while moving down the tree, when we encounter a node, we'll compare this key X with the key in that node. If X is equal to the key in the node, then the search is successful. We have found the node that contains X. If X is less than the key in the node, then we move to left child. And if X is greater than the key in the node, we move to the right child. And if we reach a null left child or a null right child, it means that the search is unsuccessful. The key X is not present in the tree. Now let's take an example. Suppose we have to search key 37 in this binary search tree. So we'll start at the root node. First we'll compare this 37 with the key in the root node. 37 is less than 70, so we'll move to the left child. Now we'll compare 37 with key in this node. 37 is less than 40, so again we'll move to the left child. Now 37 is compared with this 35. 37 is greater than 35, so we'll move to the right child. Now this 37 is compared with the key in this node. Now both are equal, so it means the search is successful and we have found our key. Now suppose we have to search 77 in this binary search tree. We'll start with the root node. 77 is greater than 70, so we'll move to the right child. Now 77 is compared with this 80. 77 is less than 80, so we move to the left child. Now 77 is compared with this 75. 77 is greater than 75, so we have to move to the right child. But the right child is null. We have reached a null child, it means the search is unsuccessful. This key 77 is not present in the tree. Now searching in a binary search tree is more efficient than searching in a linked list, because in linked list we had to sequentially search all the nodes, while here we have to traverse only a branch of the tree. So here the runtime for searching is order of h, where h is the height of the tree. This is the iterative method for searching in a binary search tree. If the key is found in the tree, then it returns true, otherwise it returns false. We take a reference p and initially make it refer to the root node. So we start at the root node and move down the tree in this while loop. If x is less than p info, then we move to the left child. Otherwise, if x is greater than p info, then we move to the right child. Otherwise, x will be equal to p info. So in that case, we return true from this method, indicating that search is successful. Now, if x is not present in the tree, then we'll reach either a null left child or a null right child. So this p will become null and this loop will terminate. So in that case, we return false from this method, indicating that search is unsuccessful. Now let's see the recursive methods for searching. This public method search returns true if x is present in the tree, otherwise it returns false. Inside this method, we are calling this private recursive method search. So now let's see this recursive method. This method returns null if the key is not present in the tree. Otherwise, it returns a reference to the node that contains key x. If this method is called with p as null, then this recursion terminates and null will be returned. If x is less than p info, then search is performed in the left subtree of p. And if x is greater than p info, then search is performed in right subtree of p. Otherwise, x will be equal to p info, and in that case, p is returned from this method. Now let's see with the help of an example how this recursive method works. Suppose we have to search for key 45 in this binary search tree. So first we call this public method search, and inside this method, this private method search is called with root as the argument. So in the first call, this p refers to the root node. So p refers to this node 54. Now 45 is less than 54. So search will be performed in left subtree of this node 54. So search will be performed in this subtree. So search is called with left child of p, which is 42. Now 45 is greater than 42. So search will be performed in right subtree of 42. So this recursive call executes. Now in this recursive call, p refers to this node 48. 45 is less than 48. So search will be performed in left subtree of 48. So this time this recursive call executes. Now in this call, p refers to this node 45, x is 45, so x is equal to p info. So reference to this node is returned from here. This reference is returned from here, and from here. Now value of this call is not null. So this condition is true. So true is returned from here, indicating that this key 45 is present in the tree. Now suppose we have to search for this key 58 in this binary search tree. We call this method. In the first recursive call, p refers to this root node. So p refers to this node 54. Now 58 is greater than 54. So we have to search in right subtree of 54. So search is called with right child of 54, which is 69. Now 58 is less than 69. So we have to search in left subtree of 69. So search is called with left child of 69, which is 55. Now 58 is greater than 55. So we have to search in right subtree of 55. So search is called with right child of 55, which is null. Now p is null. So null is returned from here. Null is returned from here, and from here. Now value of this call is null. So this condition is false. So false is returned from here, indicating that this key 58 is not present in the tree. In this video, we'll see how to find nodes with minimum and maximum key in a binary search tree. Now the node with smallest key is the last node in the leftmost path starting from the root node. To find this node, we'll start from the root node and we'll keep on moving left till we reach a node that has no left child, and that node will have the smallest key. Now node with largest key is the last node in the rightmost path starting from the root node. So for finding this node, we'll start from the root node. We'll keep on moving right till we find a node that has no right child, and that node will have the largest key. Now let's take some examples. Now in this tree, to find the smallest key, we start from the root node and we move left. Now we reach a node that has no left child. So this is the node with the smallest key. Now to find the largest key, we'll again start at the root node, and this time we'll move right till we reach a node that has no right child. So this is the node that has the largest key. In this tree, this is the smallest key and this is the largest key. Now in this tree, the smallest key is this, and this has no right child, so this is the largest key. In this tree, this is the smallest key and this is the largest key. In this tree, this is the smallest key and this is the largest key. These are the iterative methods that return the minimum key and maximum key of a binary search tree. In both these methods, if the tree is empty, then we throw this exception. Now in this method, we start at the root node and we are moving towards left in this loop. And this loop terminates when this PL child becomes null. That means this loop will terminate when we reach a node that has no left child. So when this loop terminates, P refers to the leftmost node and key in that node is the minimum key. In this method also, we start at the root node. And in this loop, we are moving towards right. And this loop terminates when P R child becomes null. That means this loop will terminate when we reach a node that has no right child. So when this loop terminates, P refers to the rightmost node and key in that node is the maximum key. Now let us see the recursive methods. This is the public method that returns minimum key of the tree. Inside this method, we have called this private recursive method. Similarly, this is the public method that returns the maximum key of the tree, and inside this method, we have called this private recursive method. In this video, we will see how to perform insertion in a binary search tree. Suppose we have to insert a new node with key value x. So we'll start at the root node and move down the tree. And while moving down the tree, when we encounter a node, we'll compare this key value x with the key value in that node. If x is less than the key in the node, we'll move to the left child. If x is greater than the key in the node, we'll move to the right child. If x is equal to the key in the node, it means the key is already present in the tree. We'll not insert it. If we reach a null left child or null right child, then we'll insert the key in the tree. Now we'll see some examples of insertion. Suppose we have to insert this key 36 in this binary search tree. We'll start at the root node. 36 is less than 70, so we'll move left. 36 is less than 40, so again we'll move left. Now 36 is greater than 35, so we'll move right. 36 is less than 37, so we have to move left. The left child is null, so we'll insert a node here. Now suppose we have to insert the key 77 in this tree. We'll start at the root node. 77 is greater than 70, so we move right. 77 is less than 80, so we move left. Now 77 is greater than 75, so we have to move right. But the right child is null, so we'll insert this new node as a right child of this node 75. Now we'll insert some keys in an initially empty binary search tree. First, this 45 has to be inserted, so it becomes a root node. 60 is greater than 45, so it becomes a right child. 55 is greater than 45, less than 60, so it comes here. 39 is less than 45, so it comes here. 23 comes here. 79 comes here. 57 comes here. 42 comes here. 10 will be inserted here. Now 34 will be inserted here. 83 will be inserted here. 29 will be inserted here. 77 will be inserted here, and 44 will be inserted here. This is the iterative method for inserting a new node in a binary search tree. In this loop, we are moving down the tree with the help of this reference P. And while moving down the tree, we are also keeping track of the parent of P. So this parent reference refers to the parent of the node referred to by P. Initially, when P refers to the root node, parent is null. And this parent is updated each time in this while loop. Now in this while loop, we are moving down the tree and searching for the key value x. And if the key value is found in the tree, we will just print this message and return. Because in that case, we don't have to insert that value in the tree. Now if the key value is not found, then we'll allocate a new node with key value x. And we'll insert this node into the tree. If parent is null, it means that the tree is empty. So in that case, we'll make root refer to this new node. Otherwise, if x is less than the key value in the parent, then this new node will be inserted as left child of the parent. Otherwise, this new node will be inserted as right child of the parent. Now let's understand this with the help of an example. Suppose we have to insert this 36 in this binary search tree. So initially P refers to the root node and parent is null. We'll move down the tree searching for this key value 36. Now 36 is less than 70, so we'll move left. Now 36 is less than 40, so again we'll move left. 36 is greater than 35, so we'll move right. 36 is less than 37, so we'll move left. Now this P becomes null. It means that 36 is not present in the tree. So we allocate a new node with 36 as the key value. Now this 36 is less than the key in the parent node. So this will be inserted as left child of the parent node. Now let's see the recursive method for insertion. This is the public method that inserts a new node in a binary search tree. Inside this method, we are calling this private recursive method. Now let's see this recursive method. The two terminating conditions for the recursive method are when P is null and when X is equal to P-info. When P is null, we allocate a new node with key value X and make P refer to this new node and then return P from this method. Now if X is equal to P-info, then we don't have to insert a new node. So we print this message and return. The two recursive cases are when X is less than P-info and X is greater than P-info. In this case, we try to insert the new key in the left subtree of P. So insert is called with left child of P. And in this case, we try to insert the new key in the right subtree of P. So this insert is called with right child of P. Now let's understand this method with the help of an example. Now suppose we have to insert a new node with key value 50 in this binary search tree. So we call this public method. Inside this method, this private recursive method is called. Now in the first call, P refers to the root node. So P refers to this node. Now 50 is less than 54. So we'll try to insert in left subtree of 54. So insert is called with left child of 54, which is 42. Now in this call, P refers to this node 42. 50 is greater than 42. So we'll try to insert in right subtree of 42. So insert is called with right child of 42, which is 48. Now 50 is greater than 48. So we'll try to insert in right subtree of 48. So insert is called with right child of 48, which is null. Now in this call, P is null. So we'll allocate a new node with key value 50. And we'll make P refer to this new node. Now reference to this new node is returned from here. Now in this call, P refers to this node 48. And the reference returned by this call is made the right child of P. So this 50 becomes the right child of 48. Next, all other calls return. And so this is how this new node is inserted in the binary search tree. Now suppose we have to insert a new node in an empty binary search tree. For an empty tree, root is null. So we call this public method. Inside this method, this private recursive method is called. Now in the first call only, this P is null. So we allocate a new node with this 60 as the key value and make P refer to it. Now this P is returned from here. So now this reference is assigned to root. So root now refers to this new node. Next we return back to this call. In this video, we'll see how to perform deletion in a binary search tree. First, the node to be deleted is searched in the tree, and if it is found, we can have three cases for that node. Case A, node has no child, that is, it is a leaf node. Case B, node has exactly one child, either left child or a right child. And case C, node has exactly two children, both left child and right child. We'll see all the cases one by one. So first, let's take this case A. For deleting a leaf node n, the link to node n in its parent is replaced by null. So if the node to be deleted is a left child of its parent, then left child of parent becomes null. And if the node to be deleted is right child of its parent, then right child of parent becomes null. Let's see this with the help of examples. Suppose we have to delete node with key 34 from this tree. So P refers to this node and parent refers to this node. Now this 34 is right child of its parent. So to delete this node, the right child of the parent will be set to null. So we write parent right child is equal to null. So now this link is broken and this node is not a part of the tree now. Now suppose we have to delete node with key 55 from this tree. So P refers to this node, parent refers to this node. Now this node is left child of its parent. So to delete it, the left child of the parent will be set to null. So now this node is not a part of the tree. Now suppose the leaf node that is to be deleted is the root node of the tree. P refers to this node, parent is null. In this case, root node will be the only node of the tree. And after deletion of this node, tree will become empty. So root is set to null. Now let's see case B. In this case, node to be deleted has only one child, either left child or right child. In this case, after deletion, the single child will come at the place of the deleted node. Suppose P is the node to be deleted. PR is a parent of the node that has to be deleted. So PR is the parent of this node P. And suppose CH is the child of the node that has to be deleted. So CH is the child of this node P. Now if P is left child of PR, then after deletion of node P, CH will become the left child of PR. And if P is right child of PR, then after deletion of P, CH will become right child of PR. Now let's see this with the help of examples. Suppose in this tree we have to delete this node 34. P refers to this node, parent refers to this node, and child refers to this node. Now this node is the right child of its parent. So this child node will become the right child of the parent node. So now this node is not a part of the tree. Now suppose we have to delete node 39 from this tree. So P refers to this node, parent refers to this node, and child refers to this node. Now this node is the left child of its parent. So the child will become the left child of the parent node. So now this node is not a part of the tree. Now suppose the node to be deleted is the root node. P refers to this node, parent is null, child refers to this node, and root refers to this node. In this case, root is updated to refer to the child node. And so now this node is not a part of the tree. In this case, node to be deleted has two children. It has both left child and right child. So in this case, first we have to find out the in-order successor of the node that has to be deleted. The in-order successor of a node is the node that comes just after that node in the in-order traversal. Now in-order successor of a node n that has a right child is the leftmost node in the right subtree of n. For example, in this tree, the in-order successor of this 30 will be the leftmost node in this right subtree of 30. The leftmost node in this right subtree is 35. So 35 is the in-order successor of 30. For this 70, the in-order successor will be the leftmost node in this right subtree. So the leftmost node in this right subtree is 72. So 72 is the in-order successor of 70. To find the in-order successor, we just have to move to the right child and then move left till we find a node that has no left child. Now the in-order successor of a node will have either no child or it will have only right child. It cannot have a left child because it is the leftmost node. Now after finding out the in-order successor of the node that has to be deleted, we'll copy the data of the in-order successor to the node that has to be deleted, and then we'll delete the in-order successor from the tree. This in-order successor has either no child or it has only right child. So it can be deleted using either case A or case B. Now let's see some examples. Suppose we have to delete node 60 from this tree. P refers to this node, parent refers to this node. Now this node has two children. So first we have to find the in-order successor of this node. Now in-order successor of this node is this node 69, and parent of this in-order successor is this node. Now the second step is to copy the data of the in-order successor to this node that has to be deleted. So 69 is copied here. Now we have to delete the in-order successor from the tree. So we make P refer to this node and parent refer to this node. Now this node can be deleted using case A because it has no child. So the left child of the parent node is set to null. Now we have to delete 40 from this tree. So first we'll find out the in order successor of 40. In order successor of 40 is 42. Parent of in order successor is this. Next step is to copy the data of in order successor to this node. So 42 is copied here. Now we have to delete this in order successor from the tree. Now this node can be deleted using case B because it has only one child. So this child becomes the left child of the parent node. Now let's take another example. Suppose we have to delete 52 from this tree. Now the in order successor of this node is node 54. Parent of in order successor is this. Now this 54 is copied to this node and we have to delete this node from the tree. And this node can be deleted using case A. This is the iterative method for deletion. It will delete a node that contains key value x. Here first we are searching for the node that contains key value x. Now after this loop terminates, P will refer to the node that contains x and this parent reference will refer to the parent of that node. And if x is not present in the tree, then P will become null. In that case, we will just print a message and return from this method. Now if the node to be deleted has two children, that is PL child and PR child, both are not null. In that case, we have to find the in order successor of P and the parent of that in order successor. So this reference will denote the in order successor of P and this reference PS will denote the parent of that in order successor. Now to find in order successor of P, we first move to the right child of P. Then we keep on moving left till we reach a node that does not have a left child. Now after finding the in order successor, the next step is to copy the data of in order successor to this node P. Now the in order successor has to be deleted from the tree. So S is assigned to P and PS is assigned to this parent reference. Now P is guaranteed to have either no child or only one right child. So it can be deleted using either case A or case B. So now let's see these cases A and B. In case B, node to be deleted has either left child or right child, and in case A, node to be deleted has no child. This code can handle both cases B and A. So first let's see how it handles case B when the node to be deleted has only one child. Here we are initializing the child of node P. If P has a left child, then this child reference is initialized with PL child. Otherwise, this child reference is initialized with PR child. Now if P is the root node, then in that case P's child becomes the root node. And if P is left child of its parent, then this child of P becomes the left child of P's parent. Otherwise, P will be right child of its parent. And in that case, child of P becomes the right child of P's parent. Now let's see how this code handles case A. Now in case A, node to be deleted has no child. So PL child and PR child both are null. Now PL child is null, so we come to this else part. PR child is also null, so this child reference is initialized to null. Now if node to be deleted is a root node, then this root becomes null because this child reference is null. Otherwise, if node to be deleted is left child of its parent, then in that case, parent left child becomes null. Otherwise, this node to be deleted will be right child of its parent. So in that case, parent right child becomes null. Now let's see the recursive methods for deletion. This is the public method delete that deletes a node that contains key value x. Inside this method, we are calling this private recursive method delete. So now let's see this recursive method. The two terminating conditions for recursion are when P is null and when X is equal to P info. And these are the two recursive cases. If this method is called with P as null, it means that X is not present in the tree. So in that case, recursion terminates. We'll print this message and return. If X is less than P info, then we have to delete from left subtree of P. So this method delete is called with left child of P. And if X is greater than P info, then we have to delete from right subtree of P. So this method delete is called with right child of P. Otherwise, X will be equal to P info. It means that key is found. And if the node to be deleted has two children, then first we'll find the in-order successor of node P. Then we copy the data of in-order successor to node P. Now we have to delete this in-order successor. And this in-order successor is present in the right subtree of P. So this method delete is called with P r child and the key of in-order successor. If the node to be deleted has no child or one child, then we first initialize this child reference and then assign this child reference to P.